Today we're going to talk about empirical and molecular formulas. Now, what do we mean by empirical and molecular formulas? Empirical formulas are considered to be the simplest formula for a compound. It's the lowest whole number ratio of elements in a compound. Because take, for instance, something like H2O2, which is hydrogen peroxide. That H2O2, those subscripts could be both divided by the same number, reduced, if you will, kind of like a fraction, and we could end up with simply H1O1 for an empirical formula, or HO. A molecular formula shows the actual number of atoms. It's the true formula for the compound. It's what the molecule actually looks like. H2O2 is the molecular formula for that substance. If you saw a molecule, if you could see a molecule of hydrogen peroxide, it would have 2 hydrogens and 2 oxygens hooked together in the molecule. So if you have something that's a compound, for instance, like C5H10, we would consider that to be a molecular. You would know that's a molecular formula because it has subscripts that are both divisible by the same number. And you have to do that on your worksheet first thing, is to determine whether a compound is for sure a molecular formula or for sure an empirical formula. In this case, that's a molecular formula. If we divided both of them by 5, we would end up with this. Technically, since ones don't belong in chemical formulas, CH2 for an empirical formula. So if we cannot divide the numbers by the same value, or the subscripts by the same number, then it's going to be for sure an empirical formula. So now, the molecular formula could possibly be the same formula. The molecule could actually look like that, but we know for sure at least it's the empirical formula. So you're going to simply do that on your worksheet. Just simply label each one of the ones up at the top of the page as being either empirical or molecular based on whether you can divide all of the subscripts by the same number or not. So if we are given information in a lab, and it tells us that we have 75% carbon and 25% hydrogen, for instance, in this lab analysis that we did, could we figure out what the formula, what the simplest formula for that compound would be? The answer is yes. The way that you want to do this is to assume. Now, you could assume any size sample you wanted to and simply take 75% of that sample and 25% of that sample and start your problem. Do you see why it would be so much easier just to assume that you have a 100-gram sample? So assume that you have a 100-gram sample. So if you do that, then getting 75% and 25% of that value would be easy. We would simply just call that 75 grams of carbon and 25 grams of hydrogen. So once we have that starting point of our ratio gram-wise, in chemistry, remember, we can't do a whole lot with grams. We really need moles in order to do calculations. So the first thing we're going to do with each of these is to divide by their molar mass. And you've probably started memorizing some of these. Carbon is 12.01 grams per mole for its molar mass. Hydrogen is 1.01 grams per mole for its molar mass. We end up with values of 6.2448. Don't round off too quickly. This is one case where you want to carry it out 3 or 4 places past the decimal, really. So that's how many moles we get of carbon, and we get 24.752 moles of hydrogen. Now, technically, I guess we could set up a formula that said, now don't write this down because it's incorrect, but we could say that we had C 6.2448, H 24.752. Yeah, I guess we could do that, but have you ever seen a formula like that? No, our subscripts are always whole numbers. So how do you change two values in a ratio to whole number values? We want it based on 1. We want the smallest value. So what we're going to do is we're going to take the smallest of these two numbers, which is the 6.2448, and we're going to divide both of these values by 6.2448. So we're going to divide both of them by that value. When we do, I strongly suggest that you carry this to one place past the decimal. You can't round these values, and you'll see why in a little bit, but you want to carry them out one place past to see that they are even whole numbers. If they're not, we've got another step to look at here in just a little bit. But if we divide the 24.752 by 6.2448, we get 4.0. What does that mean? That means we have a ratio of 1 carbon for every 4 hydrogens. How are we going to write that? We're going to write that as C, and please do this in the order it's given to you in the problem. You don't know enough yet to know how to know what element comes first, so the best thing you can do for yourself is just to put them in the same order that you had them in the problem, because I will give them to you in the order they need to be. So carbon has 1. Now remember, we don't put 1s in for our formulas. So just leave an understood 1 after carbon, and H is going to get a 4. So that's the empirical formula for that compound, CH4. Let's do a little more complicated one. This next one says we have a compound with 32.4% sodium, 22.5% sulfur, and 41.5% oxygen. And we want to know the empirical formula for that compound. So we're going to do the same thing we did before. All of those values should and better add up to 100%. So we're going to take that, assume a 100-gram sample so that we can simply say that for every 32.4 grams of sodium, there's 22.5 grams of sulfur and 45.1 grams of oxygen. And then we're going to do as we did up above in that step, divide by the molar mass, which is 22.99 grams per mole for sodium, 32.07 grams per mole for sulfur, and 16.00 grams per mole for oxygen. When we do that, we end up with 1.4093 moles of sodium, 0.7016 moles of sulfur, and 2.8188 moles of our oxygen. What was the next step? Divide by the smallest number, which is our value for sulfur. So we're going to divide all of these, a little bit of a shortcut, divide all of them by 0.7016. And when we do, we get 2.0 for sodium, 1.0 for sulfur, and we get 4.0 for oxygen. On your own, real quick, see if you can come up with the with the empirical formula for this compound. Well, hopefully you wrote it in the order it was given to you in the problem, sodium, sulfur, and oxygen. So there were 2 sodiums, 1 sulfur. Remember, do not put the 1 in for sulfur. It's an understood 1. And 4 oxygens. So that is the empirical formula for this compound. Now, what if we know the empirical formula and they also give us some extra information? If the empirical formula is this, so that's the empirical formula, but it also tells us the molecular mass, does it make sense that if this is the simplest formula, we could end up with a formula that was twice as big as this? And maybe I should be putting this in green since I don't want you to necessarily write this down. Or it could be 3 times as big as this. Or it could be 4 times as big as this. We don't know unless we have that extra information. So what we want to know from this molecular mass is how much bigger is the real compound than this one? Now, it might be the same. We might find out that the mass of the molecular compound, the molecule, is the same as our empirical formula, and then we would know that the two were the same. But what if it's not? So how do we do this? We set up a ratio, and the ratio is going to be the molecular mass, and they have to give us that. Either that or we have to have a multi-million-dollar piece of equipment to determine it. The molecular mass over the empirical mass. Now, again, what is the molecular mass? It has to be given to us, so that has to be given. How do we get the empirical mass? We have to add up the empirical formula. So we need to add up that value for C2H and Cl, add up those to get the empirical mass. So let's see what that would come out to. Like I said, we know that that top number is 181.4 grams per mole. And if we add up 2 carbons, a hydrogen, and a chlorine, we get 60.48 grams per mole. Dividing that, we end up with 3.0, or right at 3. So what does that tell us? That tells us that the real molecule, this one right here, the mass of the real molecule is 3 times bigger than that. So what do we have to do? We have to multiply everything in that compound by 3. So instead of being C2, it's going to be C6. Instead of H1, it's going to be H3. Instead of Cl1, it's going to be Cl3. So that's the molecular formula for this compound. That's what the molecule actually looks like. So let's put all of this together and add a little bit of a twist. What's the empirical formula of a compound that is 25.9% nitrogen and 74.1% oxygen? And what's the molecular formula if the molecular mass is 216 grams per mole? So let's start out with our assumed 100-gram sample, so 25.9 grams of nitrogen and 74.1 grams of oxygen. Like I said before, we're going to divide by molar mass, 14.01 grams per mole for nitrogen, 16.00 grams per mole for oxygen. So when we do that, for nitrogen, we get 1.8487. And for oxygen, we get 4.6313. Remember, our next step was to divide by the smallest, which in this case is the 1.8487. And I guess technically, guys, I should have put moles after both of these. I'll kind of squash them in here. But I divide by that 1.8487, and I end up, remember, we want these one place past the decimal to make sure they're even. I get 1.0, and I get 2.5. Now, I've seen this on the test 100 times or more, that people will often just round this up to 3. We cannot round. What this means is that the ratio is 1 to 2.5. We need these to both be whole numbers. And it's just like if we had a fraction that was 2 over 6. If we need for that to be in twelfths, for instance, if we multiply that bottom number by 2, we better multiply the top number by 2 as well in order to get an equivalent fraction for it. Same way with this ratio, we need a whole number. I always start with 2 to see if that will work. And in this case, if I multiply both of these by 2, look at what we get. We get 2.0 and 5.0. So by multiplying by 2, we got a whole number in both cases, 2 and 5. I will tell you that occasionally there is going to be one on your paper that ends up being something. It might be 1.33 or 2.33, but it comes out to be 0.3 or 0.33. What are you going to multiply that one by to get a whole number? You'd need to multiply by 3 in order to change that into a whole number. It comes out to be 3.99, which is 4.0, right? So you are going to see that on your worksheet, so be looking for it. It'll be there somewhere. There'll be one that you need to multiply by 2 and one that you need to multiply by 3. This ends up giving us a formula of N2O5 for our empirical formula. And we box it and we're ready to go, except we hopefully realize we haven't finished the problem. The next part says, what's the molecular formula if the molecular mass is 216? So we need that extra step that we just did in the previous problem. We need to get the ratio. Remember, the ratio is going to be the molecular mass, which they have to give us, divided by the empirical mass, which we have to add up from our empirical formula. So our molecular mass they gave us, they said it was 216 grams per mole. If we add up 2 nitrogens and 5 oxygens, the molar mass of that ends up being 108.02 grams per mole. So that's what's going to go down in our problem, 108.02 grams per mole. When we divide that out, that gives us 2.0. What does that mean? It means that when we write the molecular formula of this, it's going to be twice as big as our empirical formula. So we need to multiply that 2 by 4, by the 2 by 2, which is going to give us 4. For oxygen, it was 5, but multiplied by 2, that's going to give us 10. So our molecular formula for this compound is N4O10.